is something. Otherwise, it doesn't matter how we say it. Yeah. Did you already talk, by the way? Afternoon. Okay, that's good. Oh, okay, theory people. Yeah, I'm transition because I tried to make the talk less theory, but let's see. I mean, there is theory, but I didn't. I tried with no equation. Theory without equation, you know.
That's challenging.
Yeah.
But that's great.
What are you teaching? You're teaching, right? Oh, you're co-teaching. Okay, that's good. That's good.
So I taught like theory principles, but I don't have statistics.
Oh, yeah, awesome.
Yeah,
Oh, that's pretty good.
I can able to prepare slides. That's also the creative.
This is my only saving grace was Labor Day.
Yeah, that's true. Having Labor Day like for synchronous is pretty awesome.
Yeah.
Are you also teaching on Monday, Wednesday?
Monday, Wednesday.
Okay. So you
What time are you teaching?
teaching also Monday, Wednesday at 3.
Oh, 3, okay. Cool.
Great. Thank you so much for coming back, everyone. And for this morning session, we have our last speaker. So let me introduce like Professor Samet Oymak, and also from the University of Michigan in its department. And Samet research spans the optimization, statistical learning, and decision making, and also with very interesting applications in the different side. So I can say, as I just talked with Samet, this is really some pretty good combinations of the theory and applications you will see in this talk. And prior to UMich, and he was also the ECE departments at the University of California in Riverside. And he has also spent time in the industry at the research experience as a researcher, and also did a postdoc at UC Berkeley as a SEMA's fellow. So this is really great experience for the SEMA to across like both industry and academia. And also SEMA received like the NSF Career Award and also multiple other industry faculty research awards, and also something else. So let's welcome Samet for giving us the very good talk. Thank you so much.
Okay, yeah, from the beginning. Awesome, yeah, okay. Thanks for the introduction, Liu. And so first of all, thanks Ching and Liu for organizing the fantastic workshop. It's a great pleasure to be here. So today, I will talk about some of our recent work on language model or sequence model architectures. So let's get started. Like I want to also, I mean, the other objective of the talk is kind of providing some context on, at least like, in my opinion, kind of what is going on. So let's see if the clicker is clicking. Anyway, I guess I don't need a clicker. I can click myself. Oh, okay, oh, okay, now it should click. Okay, cool. Yeah, so basically, I mean, the point of the talk is basically essentially what is a language model architecture and what makes it kind of different than, some other architecture, right? So, and to do so, like, we can essentially think, okay, what's happening traditionally, right? I mean, obviously, neural networks sound complicated, but the simplest possible neural network is essentially a linear regression, right? I always think, okay, linear regression is the most basic neural network. And the linear regression has been around probably since 1800s, right? And then if you think about some other linear models like logistic regression or perceptron, right? They are around at least since 1950s, right? And like there are a bunch of essentially 1950s to 2010s, there are already a bunch of like pretty good neural network architectures. And in fact, like all these like important architectures such as convolutional networks, they have already been proposed by then. And then since 2010s, there is deep neural networks, there is like more computation, more data. So basically, the more data you have, you want to increase your network size so that it can learn better, right? So, but since 2018, right, 2018 to now, essentially, there's this paper, like attention is all you need. And it is kind of essentially driving, like, at least like conceptually, it is driving a lot of like architectural innovation. Like basically, we are moving from more classical neural networks, at least in the context of language and sequences, to essentially a new class of neural networks. And this also often underlies foundation models, because foundation models, especially when they're multimodal and when they're interacting with humans, there is a language component involved. And whenever there's a language, typically, your architectures are either transformer or some efficient variants of transformer. And what I mean by efficient variants of transformer is, for instance, transformers using Softmax Attention. These efficient sequence models are using some essentially more compute efficient approaches, okay? But the question is basically, okay, like what makes these architectures different than these models? Because I personally like linear regression best. Like I always consider my career is built on linear regression. So, I don't want to move to like something super complex, but it's fine. So I just want to go briefly, like, what are the key differences between pre and post transformer? So there are a couple of key differences, right? And it can be like, this might be subjective, but this is kind of what I think, right? So one key difference is obviously tokenization of data. We are essentially, we are either dealing with sequences, or we can patch the images into small tokens. So we are treating data as a set or sequence of tokens. Secondly, these data-dependent layers. So I will discuss in a second, but what I mean by data-dependent layer is that when you are dealing with a neural net or linear model, right, your weights always multiply the features. Whereas this new class of architectures, there is essentially explicit feature products. And finally, and I will discuss less of this, I will not discuss about the computation aspect. There is essentially a lot of system level considerations. So it's not about the theory, but it's about like how to make sure like the training is parallel. How can we essentially fit like potentially train a model with trillions of tokens while making it as efficient as possible during inference as well as training. So the discussion in this talk will focus on essentially kind of more statistical or optimization aspect and not the systems aspect, which means I will discuss essentially this sequence aspect, tokenized sequence data, and the data dependence. So first, let me explain what I mean by data dependent layers. So this is essentially a picture of a standard like deep neural network. And if you look at essentially what this is doing, it is simply like repeated feature matrix multiplication, feature weight matrix multiplication. So basically we are taking features X, multiplied with W1, get new features, multiply with W2, and so on. So this is, and linear regression is a special case of this. Again, if you are doing only one shot, then it is just a linear model, basically. So what is the difference between modern neural networks? Like what do they bring to table? So essentially what they bring to table is basically explicit feature products. So, and this explicit feature products comes in two forms. Either like there's so-called attention mechanism, and there's also so-called gating, okay? And these sounds like fancy words, but essentially it is just mathematical formulas. So what is attention mechanism? And this is essentially the canonical attention, but it doesn't have to be Softmax here. But so the idea in attention mechanism is that you have a sequence X, and you essentially project elements of X into different subspaces and explicitly product them. Essentially, I take X, and in this layer, I multiply Q features with K features, and then take the result and multiply with V features. So it is explicit feature product. It's kind of a third order, kind of like if you remove the Softmax, it is a third order polynomial. So a standard neural network does not create that, right? Whereas attention is creating an explicit like third order polynomial in some sense. So another important building block is gating. And gating just means basically kind of Hadamard product. Take two vectors, and if you entropy product it, then you can call it gating. So this idea goes back to LSTM. And the most basic gated block can be considered to be gated MLP, okay? So if you have a one-layer neural network, everyone knows what it is. It is like some nonlinearity plus like project, like linear multiplication and nonlinearity is one-layer neural network. If you also apply entropy dot product with another output of the one-layer neural network, that's the kind of basic gating block you may imagine. But more recently, essentially, in recent architectures, people are throwing gating like all over, basically, left and right. Let's add gating to see, like, as I will discuss in a second. So one special instance, which is an important instance, is like this class of architectures gated linear attention. So this linear attention compared to Softmax attention has computation efficiency advantages, but if you just do linear attention, it doesn't work that well, okay? And we will get to its reasons later on. So, but many popular architectures are special instances of gated linear attention. So this includes basically, like, as you see, like, there are a whole bunch of architectural proposals, and all of them are essentially, sooner or later, what they are doing is a gated linear attention. So essentially, this kind of highlights the abundance and importance of gating in sequence modeling. And again, the key idea goes back to LSTM, but one drawback of LSTM in this age is the fact that it's not parallel computation. So all of these architectures are also parallel, and like, I will not get into details too much, but it relies on the fact that this gating depends on the current token rather than the state. So it kind of allows for this like parallel scan type parallelized algorithms. So another critical thing is that, again, just to mention, GLA admits a recurrent representation, which means that during inference, like compared to standard softmax attention, it can be more efficient. That's why, like, it has favorable properties. Like, inference is kind of order 1 in the dimension of state. I mean, in the sequence length, not dimension of state. So it doesn't get impacted by the sequence length. Okay, so overall, basically, if you essentially gather these ideas all together, you can essentially make a table, and the table you can essentially look at like all kind of state-of-the-art sequence architectures, right? And you can see that basically they have like they have either, there is no architecture without attention or gating, right? Any architecture that is useful for, let's say, language modeling, it either includes attention or gating. There is no basically standard neural network with weight feature multiplication, basically. So essentially, the success of attention and gating highlights, the broader architectural principle of, okay, maybe like what we need is like, it's not attention is all you need, but explicit feature product and data-dependent sequence mixing is what we need. And that's, I believe, like where the community is going as well. But on the other hand, there is like much less theoretical understanding also. Like, empirically, I think we are getting there for sure. So in this talk, like what I want to discuss is like, I will discuss some of our work regarding the theory of like gating and attention, right? And also, like, can we use some insights? For instance, like, let's say I'm using attention, maybe what kind of bottlenecks gating can address? And in terms of the bottlenecks, I will also discuss some upcoming work. For instance, we introduce like gated Softmax attention to like, essentially it's a very like low cost change, like that you can fine tune on any model like Llama 3, and then it improves essentially the architectural performance. So the outline is 3 ways. So we want to discuss theoretical understanding of attention and gating. So first, like I will go over our results on essentially what is essentially the canonical transformer model trying to do. When you optimize the model, what does it learn? Secondly, I will discuss some shortcomings of canonical transformer, and then what if we add some principled gating and how it can essentially address these shortcomings. And finally, I will also discuss the linear attention and gating through essentially kind of like algorithm learning or in-context learning viewpoint. In other words, like if I want to understand the role of gating and linear attention, can I design some toy problems to interpret what they are doing? So this is essentially the outline. So let's start with the first part. So in order to motivate the first part, what I will do is basically so I will try to essentially visualize a like very simple like conceptual problem, okay? And so this problem can be like this transformer as bird hunter, okay? Like this is kind of all like fake pictures here. So suppose like I have a picture, right? And suppose in this picture there are a bunch of like bird images, and there's also a background. And again, the goal here is basically kind of understanding like what would like when I train a transformer, what is essentially the model inherently learning. So what I want to do is like I essentially want this model to hunt the birds in some sense, right? So that corresponds to, in other words, like what I really want to do is basically I want to build a model that can essentially, these are patches of the image. So these are essentially kind of like tokens of the sequence. So each patch that you see, this is a 5x5 square, it's tokens of the sequence. And we just want to check mark those tokens if there is a bird on them, okay? So it's kind of a selection process. So how can we do this? So in the context of transformers. So basically what's happening is that, I mean, at least in this picture it is very clear. In general, it is not that clear. But you can essentially, when you look at this picture, you can essentially think, okay, there are some relevant patches, right? And irrelevant patches. I mean, here it's super clear. Like when you're doing the theory, it is less clear what is relevant or not. I mean, you need to define it rigorously and so on, right? But in this context, it's super clear. And if I want my model to be successful, and if I want to answer essentially this question, let's think essentially what I want to do, like as a human. So as a human, like I want to do kind of like feature selection or patch selection, right? I essentially have a patch classifier in my head, and then my patch classifier will essentially split the relevant patches and background. So what I want, so basically during training or like at the end of the training, what I want to have a kind of a 0-1 mask that will essentially figure out where the patches are. An important thing is that basically how does essentially transformer does this? How does this process work? So transformer or like standard Softmax Attention assigns a probability to each of these patches through Softmax, because each patch has a score, and when you pass it through Softmax, you get a probability. And high probability means that patch is good in some sense, and low probability means it is not good. So as a result, basically, ideally, if you think very like basic, right? You want like essentially the selected patches, you want their Softmax probabilities to be 1 over number of birds. So they are essentially all the selected guys. And the background should receive 0 probability. 0 means like it is gone. And like otherwise it means 1 over number of birds means the total probability adds up to 1. So this corresponds to such a process, right? Intuitively, basically, when I'm training the model, like this, there is initially empty mask, and this mask suddenly appears like during training. Ideally, that's kind of what I want to formalize. So indeed, like empirical insights, like if you essentially run a real model, so this is essentially what you see. So as you train the model, like train the model like during optimization and pick an image and see like what is its attention map, let's say for the classifier token. So essentially during the training, let's say if this is the input image and you are essentially progressing through the epochs, which means you are training longer and longer and longer, you can see that basically at the start, there is no model. The model is just a random decision, right? And the attention map is like super diluted. But then as you train longer and longer and longer, attention map concentrates, and there is essentially this kind of token selection happening, right? There is essentially a bunch of tokens, like each square is a token, and you're essentially selecting fewer and fewer tokens. So this is essentially in line with the intuition, right? Because intuitively the model is trying to select the center or the most frog-related squares or patches. And not only that, during this process, what's happening is that the sparsity level, which means like let's say L1 over L2 ratio, sparsity level is increasing during training. It's becoming more and more sparse, and in some notion of soft sparsity basically, or spikiness. And during this sparsity level is essentially, it's becoming less sparse. In other words, there are fewer selected tokens. And at the same time, what's happening is that the model weights are increasing. And this is also in line with intuition, because if you know what is the Softmax function, if you want to saturate it, if you want to select very few, if you want to make it 1 or 0, you need to make the input of the Softmax very large, basically. There should be some saturation. So this is kind of in line with like the basic intuition, okay? So, but in terms of theory, basically what we formalize, and I will not get into all the details ins and outs of the theory, so as a result, it will be kind of a non-rigorous statement here. So, but suppose like X is a input sequence of T tokens. In this picture, there are 25 tokens. There are 25 patches in this picture. Each patch is a token that essentially I treat as a set or sequence. And then I essentially want to, like in our works, basically we studied basically what is the behavior of the key query weights. So basically we combine the key embedding and query embedding weights into a single matrix, which is combinable, no problem. So in that sense, basically Softmax attention operation takes this form, okay? So basically I have this attention X is equal to Softmax XWX transpose. These are the similarities between the patches, and this is the input. Essentially, Softmax attention maps an input sequence to an output sequence based on similarity scores. So essentially for each patch, you compute some similarities and then you create an output sequence. And then we ask basically kind of, okay, like, So if you train the model, what will happen, right? And we can define a training problem. And this training problem is basically any kind of loss function. I will not get into the exact details of what we assume in the theory and so on, right? Like for instance, if you are assuming classification, then you need a label. If you're assuming next token generation, you need a next token and so on. But let's discuss an arbitrary loss function to keep things general. And then we essentially ask ourselves what happens during gradient descent, which means I am training this model one step at a time during a standard first order method, which is the typical practice. And two key questions, right? One question is, can I analytically characterize where WGD is converging? Number one. So I just optimize this starting from, like, let's say 0 or some random, and that's the first question. And what is the interpretation? Like, for instance, does it align with the intuition we discussed? So we studied this problem in multiple papers. And then I will just summarize the main takeaway, rather than going over papers one by one. So basically, the main takeaway is that we essentially provide a decomposition, okay? Basically, as the gradient descent proceeds, like suppose like you run the iterations many times, right? The optimization is essentially converging to somewhere, right? At the point of convergence, right, what's happening is that the weights are decoupled into two components. It's called W finite and WSVM, okay? And the nice thing is that they admit analytical characterization, which means basically I can literally solve for instance, like convex optimization to figure out what are these weights. And then the interpretation is as follows. So WSVM part is the so-called directional component, okay? This part is going to infinity if it exists. It doesn't have to exist, but if it exists, it's going to infinity. And the role of this part is inducing a 0-1 mask on the tokens, which means it literally acts as a hard token selector. And the second part is the finite component, and the role of this guy, WFIN, is it allocates the importance levels of the tokens, okay? So basically, this is essentially literally like describing what attention is doing, because if you think about Softmax Attention, it can presumably select as 0-1.
I have a quick question.
Yeah.
Are you assuming that the number of keys that you're using is 2 in this analysis, or you're assuming an arbitrary number of keys?
So okay, I see. So basically, for most of the theory, we assume there is a single query. In other words, we are reading a single output rather than sequence to sequence. Yeah. Single query, but keys and values are the full sequence. Yeah. Okay, so basically allocates the softmax across the tokens, right? So pictorially, basically, what we are formalizing is this picture. So this is what we discussed, the hard token selection, right? And what we are essentially also showing is that basically on top of the hard token selection, you also have this adjustment. And this adjustment, imagine the following, right? Maybe some birds look more like birds, and some birds look less like birds. So basically, depending on that, maybe you want to select more of those birds and combine in your final score or final token, basically, output. So a couple of nice things here is that one is like, I mean, as someone with like this compressed sensing background or sparsity background, right? I do believe, like, as Ching was discussing as well, right? Low dimensionality, for instance, right? Either low ranks or sparsity. Like, I think these are like super important concepts, right? And indeed, like, basically, my interpretation as someone with like compressed sensing background is that, okay, essentially this is kind of a lasso-like behavior, L1 regularization, right? But lasso is kind of induced by the saturation of the softmax in some sense. And there are a couple of interesting things. So one is that, so basically there is theory, and this is essentially like formal in certain settings, but in many settings there are essentially a lot of open problems, and I will not get into that. Like one open problem is, for instance, like under what conditions, like as the data increases, for instance, you would expect a transition from some hard selection to full soft selection. So, but yeah, I mean, in the interest of time, I will skip those. So another visualization is this. So basically, I have been discussing what is this WSVM, support vector machine, okay? So support vector machine essentially is, in the context of classification, the goal of support vector machine is separating plus labels from minus labels. Here basically what's happening is that we are separating different chunks of the input rather than separating two input labels, like some plus example from minus. We have one input example with a bunch of birds, and we are separating internally what's happening inside it. So it's a feature selection process. So basically, these are the good patches and these are the bad patches. So in some sense, there are a bunch of grass here and there are a bunch of birds. And we are essentially learning the max margin separator. That's kind of what the theory is advocating. Okay, so this essentially summarizes some of our work on transformer optimization theory. So next, I want to discuss some bottlenecks in self-attention and how we can potentially improve it. So basically, as we just discussed, right, sparsity is like super important, and it kind of like helps us formalize this token selection, or like how the model attends the relevant pieces part, right? But one thing is that basically we also discussed, for instance, if the model is getting, the attention map is getting more sparse, then the weights should grow, right? This is essentially a very basic property of Softmax, because like sparse attention map, you have to grow the weights. Like there is just kind of no other way around it. So now like consider the following like potential bottleneck. So attention map, like perhaps like, you know, let's consider language, right? In the language, there are a bunch of different words. Like should, let's say different words is their attention map similar sparsity or different sparsity? Perhaps like, you know, some words deserve to attend more tokens in the context and some words deserve to attend less tokens. Or, you know, it can be more general than that. For instance, it can also be position dependent. So the example I had in mind is like consider a word like salmonella and bacteria, okay? So basically bacteria is kind of a more public phrase, right? Whereas salmonella sounds like a more technical phrase. So if you look at the cosine similarity between these two words, salmonella and bacteria, because the first one is a special type of second one, you would expect high cosine similarity between them. But on the other hand, in other words, they should have some semantic similarity, right? But on the other hand, the first word, because it is more technical, in the context window, maybe it will attend to less words because it's kind of a technical and niche thing. For instance, let's say if I say Barack Obama, right? Let's say Barack. Once I say Barack, it should probably go and attend Obama in the context window. It shouldn't try to attend, let's say, Cucumber or something, right? So basically, whether you buy this or not, right? This is kind of the starting intuition. And based on this intuition, now consider the following, right? So if essentially there's this variations in contextual sparsity, then in order to represent essentially a bunch of different tokens with a bunch of different desirable sparsity levels, I'm still using the same weights, which might create problem. Because those same weights should have to be sometimes large, sometimes small. It might create some difficulties. And this is especially so if the semantic meaning is closer. Basically, you can prove that if the semantic meaning is close, but the sparsity levels are different, it creates an optimization bottleneck. Like the model cannot express it, basically. This is, I mean, under very mild conditions, this is provable. So the basic idea we had is like, okay, like, why can't we essentially control the sparsity explicitly so that like the model has an easier time kind of like representing, kind of focusing depending on the word, okay? So what we do is like, this is essentially the typical picture of Softmax Attention. So you have this like WKQV projections, and you apply Softmax and so on. So what we try is essentially the following very simple modification. For the query and value, and we don't use it for key. So I will not explain the intuition behind, but like it is not as useful for key basically, but for query it is useful because query is essentially, suppose like I'm at the token salmonella, that's the query token, and I want to adjust its sparsity level explicitly, right? So I need essentially a kind of like a temperature scaling there. That's the intuition to make the Softmax spikier or less spiky. So this is essentially the proposal we have, like very simple adjustment to standard transformer architecture. And it's also super efficient in the following sense. Essentially, we take a query token Q, and all we do is basically a vector dot product. So there is no matrix multiplication. It is just a vector dot product. We tune essentially a WQ vector and WV vector. And it is just a essentially vector dot product and enterprise dot product. So basically, it's kind of the cheapest possible operation in some sense. And then we tune this WQ and WV. And another nice thing is that you don't need to train the model from scratch, right? You can essentially download any kind of like Llama 3 model with 400 billion parameters, and you can just fine tune it on it. So essentially, before kind of discussing empirical results, we can essentially get some intuitions. So one intuition I personally like more than empirical result is like this. suppose like you have 8 tokens in your vocabulary. In other words, rather than let's say 100,000 in English, like you have only 8 words. And suppose like we kind of like create we provided like essentially latent attention maps that we want to learn. So the question we are asking is basically, okay, like how well the Softmax attention versus this approach, gated approach, will essentially approximate ground truth attention maps. So it turns out basically, if you essentially create this weighted attention map, like in another paper, essentially we discussed this issue. So there is a one-to-one map between one layer attention maps and a Markov chain. So basically this 8x8 matrix you create is essentially a Markov transition matrix. So essentially in this experiment, in the simple experiment, like this is the ground truth Markov transition matrix. We just put it ourselves. This is essentially what we want the model to learn. So here, like each row is one attention map. Basically for each token, there is an attention map of size 8, and there are 8 tokens like that, 8x8, which captures all possible word transitions in some sense. So it's a Markov chain transition matrix. And it turns out, if you essentially try to learn this Markov chain transition matrix with standard self-attention, under the assumption that model is, let's say, low rank, which happens in multi-at attention, it is not able to approximate the ground truth map. It's like, it is essentially creating a poor approximation. Whereas essentially, if you add this gating, right, cheap gating, just the scaling of the attention predictions, then you have a much like more fine-grained approximation. And it kind of makes sense as we discussed, right? Because like there are a whole bunch of different sparsity levels. If everyone was attending themselves, it would be much easier. If the sparsity level was 1, then you can just learn the identity map and you're done. Like both of them can approximate. But if the sparsity levels exhibit variation, then problem becomes more difficult, basically. Okay, so then like essentially we can go ahead and evaluate actual LLMs. So I will skip this a bit fast, but so essentially we did some pre-training perplexity evaluations. Some of like this paper is still not out, so it will be out soon. So there will be better evaluations hopefully soon. But like we essentially tried Llama 3 or Pythia, and it improves pre-training perplexity, reasonable amount, but not a lot. Like I mean Llama 3 improves more. I think Pythia improves less. So I think we also observed like more improvement on reasoning benchmarks. Basically, these reasoning benchmarks like Pika or like Arc Challenge and so on. So basically here we observed like more significant improvement. And I believe one reason, I mean this is very speculative. I mean there is no grounding for this, but like my personal belief is that for reasoning, this like hard attention or ability to implement like discrete process is more important. And because essentially we are able to provide a like better approximation to discrete map, discrete 0-1 transitions, that might be why essentially for reasoning benchmarks or actual LLM evals, like how it performs rather than pre-training, it has more benefit. And the theoretical insight here, like the summary is that we are trying to decouple the semantic similarity, right? Salmonella and bacteria. These two words are semantically similar. But on the other hand, maybe they deserve different contextual sparsity levels. So basically, in terms of like this theory is not that complicated, right? But in terms of like approximation, what you can show is that basically if two words are semantically similar, but they deserve different sparsity levels, then standard Softmax cannot approximate it well unless the weights grow a lot. And once you essentially do our approach, weights don't have to grow. And in fact, like we verify this empirically as well. Once you do our approach, weights, like attention weights are kind of much smaller. Okay, so the final part of my talk is like understanding kind of like this. So basically we have so far focused on Softmax. So I will also discuss this linear attention and gating. It's kind of also related to the kind of more recent proposals such as GLA and Mamba. And to do so, I will discuss some of our results on in-context learning. And in context learning, essentially what I will discuss is kind of like, I mean, the sequence models. One reason this sequence models potentially require these attention or gating type operations is that for reasoning tasks, where like you essentially have this semantically meaningful tokens and you want to interact them, right? So you can essentially learn algorithms, and algorithms that you are learning might benefit from these explicit feature products, basically. So this is, I mean, at a high level, this will be the kind of like intuition. So, but before that, let's discuss what is in-context learning. So in-context learning is essentially kind of like the following problem. It is essentially the problem of learning a latent function from the data provided in the context window. So it looks like this. Suppose like, I have a ChatGPT model or any kind of model, right? I feed basically these examples, apple, manzana, banana, platano, and pineapple, right? And then I expect the model to figure out basically the latent function, latent map between the first and second token, which is the function English to Spanish. So basically the model should figure out English to Spanish function and then apply it on the final query. If I essentially, and then it should tell me this. If I repeat it for another sequence, Japan, mochi, and so on, right? In this case, the model, there's another like underlying function. The function is counter to dessert. Given the country, output the dessert, right? So rather than training the model, I want model to figure it out itself from the data provided in the context window. That's what is in context learning. And if you want to generalize this function, English to Spanish or country to dessert, in the context of language, it sounds abstract. How can we formalize this? But you can essentially view this as a basic machine learning setting. There is a x and there is a fx. There is a x and there is a fx. And you want the model to infer f and then apply it on the query. And you can see why like now like this explicit token interaction can help, right? Because like the easiest estimate of f, the linear estimate of f is basically literally multiplying x and y, and that creates kind of a linear estimator. And this is essentially what we will discuss. Even if f is nonlinear, even if like, this counter dessert sounds super complex, if you simplify things enough, it becomes actually kind of a linear model, which is, my turf, basically. So, yeah, basically this is the setting. And then clearly, needless to say, this in-context learning is kind of an important step for like this formalizing reasoning or algorithmic capabilities, right? Because if you are essentially able to infer a function from the context window, it means you are kind of applying a learning algorithm to figure out f, okay, right? So it is inherently related to like algorithms and reasoning. So again, let's drop the language. Let's go to essentially this simple setting. So in this simple setting, what happens is that let's essentially consider a linear model. And then in this linear model, I have my prompt sequence. So I will fit the model x1, y1, xn, yn, and xn plus 1. And suppose the model is related by an underlying function, beta. So basically, xi transpose beta is my fxi. That's the setting we are discussing right now. Okay, and the goal of the model is in some sense implicitly figure out beta and try to predict xn plus 1. So this is essentially a very, very, very simplification of what we just discussed in the language context, because the function is kind of a very clear, understandable function. So the goal of the model is predict yn plus 1, and then we essentially minimize the training loss. So basically in this, for the following discussion, again, I'm focusing on optimization, and let's minimize the training loss, and we're essentially fitting a model to explain this yn plus 1 prediction. So that basically this model that I train becomes good at in-context learning, right? Because, when you are doing language modeling, you train the model on whole internet, and it becomes good at in-context learning of, let's say, language tasks. So the question we ask is, like, can sequence models, let's say, Softmax Attention, linear attention, and so on, can they solve this problem, right? And then, if so, what do they learn during optimization or training? And intuitively, again, let's start as a human, what would I do? If you tell me this problem, what I would try to do is basically given these x vectors and y vectors, right? I would create a system of linear equations and apply pseudo-inverse, get my beta hat, and apply on xn plus 1, and I'm done. This is what I expect when I give a qual exam. So this is the ideal scenario, okay? And then it turns out basically what you can construct. So basically, there is these different stages of machine learning, right? You can essentially ask like what you can approximate, what you can learn from finite data, and what you can optimize. So it turns out the following construction is not that difficult. You can construct a multi-layer linear attention that iteratively solves for beta via gradient descent. So I can essentially construct a multiple layer of linear attention network, okay? So that each layer of the network will apply one gradient iteration on beta on this data x and y to figure out the implicit beta. And then at the end of multiple layer of iteration, I applied L gradient descent and then predict the token, okay? I can explicitly run linear gradient descent using my model. That's the takeaway. So in this context now, in order to provide our results, I need to describe what is gradient descent and this and that, okay? And I will only focus on one layer models. I will not try to get it complicated. So if you essentially take one gradient descent iteration, and we will focus on this preconditioned gradient descent. You can also essentially adapt the gradient descent to the structure of the data. So the preconditioned gradient descent takes this form. So you apply the first iteration starting from 0 is x transpose y. So this is the first iteration. Given labels and input metrics, you apply x transpose y, first iteration. And then you can apply a preconditioner w to reshape the prediction to make it more amenable to prediction. So basically my implicit beta hat here is basically beta hat equal to this. After I construct beta hat implicitly, at this here I'm constructing explicitly, but the model will construct implicitly, right? So I construct this beta hat and then hit with xn plus 1 to make a prediction. So this is essentially what prior works focus on. We also focus on this, we will also discuss this one-step sample-weighted projected gradient descent. And sample-weighted means basically, rather than applying just a preconditioner to shape the features, what if different samples have different importance levels, okay? Maybe I'm doing gradient descent, some samples are noisy, some samples are not. How do I deal with that? You can essentially weight every single sample in the context we know with a coefficient omega I, and that becomes like WPGD, weighted projected gradient descent. And the prediction is beta hat, and then I hit beta hat with the, this is the model estimate, and I hit with xn plus 1. So basically the results are as follows. So linear attention has been subject of quite a bit of study, as we discussed, right? And essentially if you optimize linear attention with in-context learning objective, at this point it is well known that basically it learns projected preconditioned gradient descent, which means essentially the optimal linear attention, this is not an approximation result. Approximation is trivial, but when you optimize the model that optimizes the loss landscape is truly one-step gradient descent. Okay, it's true with the optimal preconditioning. So what we ask ourselves is the following, because the point of this talk is this gating and bunch of different architectures, right, and how they are faring off. So we focus on, for instance, a state space model, like H3 model, and this model applies double gating. I will not get into the details too much, but there is double gating here. There are 3 channels just like linear attention, but rather than multiplying them, you are gating them, and you're also applying convolution in the middle to mix the sequence. So basically this F is implicit in the state space models and explicit in gated convolution models. So basically it captures a bunch of models. So what we can prove is that if you optimize the ICL objective, now you are no longer learning PGD. Under mild conditions, it's probably learning WPGD. So basically the optimal function, and this convolutional filter is providing weighting, basically. That's the intuition. So now essentially we have a larger class of algorithms that we are learning. So basically this is the first insight, right? And the second insight is that under mild conditions, in other words, if you focus on what earlier works focused, right? Like essentially this more simple data model, then under the data model, actually they are exactly equal. Both of them are learning PGD because samples have no different importance levels. So you will literally learn optimal weighting of omega equal to 1. So another key insight is that basically this gating and attention, I have been discussing this too, right? But it turns out, for instance, in this context, they are exactly equal in the optimization landscape sense. So it seems like they are different architectures, but they are doing the same thing, right? So basically, it points to this universality of explicit feature dot product, because some call gating and some call attention, but they are kind of end up being equivalent. So I will just quickly go through experiments and wrap up the talk. So basically, indeed, if you look at the previous work setting, this is essentially a standard setting previous works use. They are indeed exactly equal, SSM and linear attention. And if you essentially focus on a non-trivial, less trivial setting, where let's say there is a temporal shift, maybe beta vector is not fixed, but it's shifting over time, then actually you need to weight the context window differently because the recent beta is more important. And then you can see that actually SSM is doing better because it can better adapt to temporal shift using the convolutional filter. Okay, and finally, I just want to discuss gated linear attention, okay? So far we have been applying this gating outside of sequence mixing. So basically all these like architectures, like recent architectures such as GLA or Mamba or XLSTM, whole bunch of state-of-the-art architectures, they are applying mixing within the, like they are applying gating within the sequence, okay? So linear attention is essentially this recurrent formulation. I will not get into that, but this is essentially why it's kind of more efficient. And gated linear attention is essentially applying gating to this recurrent formulation so that you can selectively forget the past or keep the past. It is just like the LSTM idea, right? If you think about this RNN versus LSTM, it is the same idea. But the key difference is that gating depends on the state, the current input, not the state. In LSTM, it depends on the state, which kind of breaks parallel computation. So you can ask essentially now, you can similarly ask what algorithm one layer GLA is learning, right? Because now there's even a more complex model. Like, because we have been discussing linear attention, but what is this like more sophisticated thing learning, right? And the answer, I will spare you the details. So basically, now we have this class of algorithms, right? Projected gradient descent, weighted projected gradient descent. But so far the weighting scheme is fixed. It's not data adaptive, right? So basically for gated linear attention, it is essentially learning a data dependent weighted projected gradient descent. So essentially the critical aspect is the fact that the weighting scheme is data dependent, which is essentially kind of trying to imitate softmax, right? Because softmax can selectively figure out the good birds versus background, which is the grass, right? Bird versus grass. So I want my, essentially, the model to be able to do that. And the standard models cannot do that because the weighting scheme is fixed, right? It always like apply the same weighting at a particular position. Whereas if I make the gating depending on the bird versus grass, right? I can potentially do that. So just to wrap up, the goal of, so basically we discussed essentially some theoretical and empirical understanding of modern sequence models. So I would say basically the current evidence says that gating and attention or basically explicit feature products are pretty important. And this is essentially what we need, right? So for Softmax Attention, we provide the optimization landscape characterization. I mean, I did not provide too much detail, unfortunately, but the key takeaway is basically this, I think, this decomposition and hard token selection. And there are a bunch of other like discussion here, like there's essentially very nice graph theoretical connections, like if you were doing next token prediction, but you know, like in the interest of time. So we discussed how like sparsity controls, this sparsity is important and how we can control it better. And then we also discussed how like these algorithmic tasks, especially for sequence modeling, right? They are important, this in-context learning, how the model can implicitly learn a learning algorithm, how essentially they can inform the capabilities of like sequence models. And the takeaway was that basically simple linear attention is PGD. A more sophisticated version is the weighted PGD, but this also says that basically gating and linear attention can be equivalent with suitable application. And then, for instance, more recent architectures are essentially can implement these data-dependent algorithms, which is critical for success. I would like to thank all my collaborators and funding agencies. If there are any questions, I'm happy to take.
Thank you so much, Samet, for the very terrific talk. We have seen a lot of very interesting observation study on like important concepts like attention gating and also the concept learning. Okay, let's see if there are any questions from the audience. Okay, I will go the first one and people can take something to think about. I think these are pretty cool to have this kind of analysis with like either the empirical insights and also the theoretical study. I wonder like in this kind of case, so after we observe this kind of the different like the conclusion from this kind of theoretical study, so how do you think if we design some like specific transformer-based model for some specific modality in different applications? So what would be your suggestion or your takeaway to think about what will be a more efficient transformer-based backbones that we can design in some specific application?
Yeah, I mean that's a good question. I mean actually that can be a pretty like applicable question. So I guess like I mean it's possible to perhaps like in the network, again this is kind of an empirical answer, like this is but it's possible to perhaps like in a pre-trained network maybe one can identify like kind of the saliency of different spots, like just like for instance when you train a model, like you often want to understand like the saliency of individual features, feature importance, right? Perhaps like there should be some understanding of okay these building blocks are important, right? But like how to place them, right? There is essentially, so right now basically there's a lot of like whatever works better, right? There could be some more better principled understanding of okay, let me just essentially kind of like insert this atomic block and kind of quickly get an idea of like how it will impact, like in a very very quick fashion during fine tuning. So perhaps like something like gate tuning, let's say, right? Because like maybe like your gating strategy is not good for one modality but the other, but you can literally take existing model and quickly fine tune it. So I guess the point is that we still want to use the pre-trained architectures. We don't want to deviate from them too much. And just like the example I provided, right? You can literally take Llama 3 and you can just add small blocks on it, right? So if you can quickly identify the important scores of where to add, then maybe like we can have a better route.
I see. And also a quick follow-up. So what you're talking about here is mostly for the single modality, either.
This is single modality, yeah.
Exactly.
It is, yeah.
And here we have also seen the works like using tokenize everything for a cross model, like or multimodal learning.
Yeah.
Also using like the transformer-based backbone. So do you think this kind of the study or phenomenon or what observation we have here is also generalizable for that kind of case?
Oh, I see. So yeah, indeed. I mean, this is a good question. Actually, like perhaps like I mean maybe the current, at least like the research I'm aware is more focusing on in single modality, right? So if there are multiple modality, perhaps then maybe there are some basic architectural principles where like how you want to add the attention or gating to merge the modalities. And there can be some actually multimodal building blocks in that sense. Rather than single model building blocks, maybe we need multimodal building blocks. Yeah.
Yeah, exactly. I think there are some debates like shall we use cross-modal, cross-attention or self-attention for this kind of cross-modal. Yeah.
Yeah, I think this is an excellent question. Yeah. Now I understood better. Thanks.
Okay, great. Yeah. Any other questions from the audience? Yeah.
So for the attention map decomposition, so you have a mask matrix and like a weight allocating matrix, right? On the first line.
Yeah, sure.
No.
Okay. You mean this part?
Yes.
Okay.
So why do you want to use additive decomposition? Because it looks more like a multiplicative decomposition to me.
You're asking this, right?
Yes.
Yeah. So basically, so this is essentially, this W is essentially multiplication of WQ WK transpose, right? And suppose they are full dimensional, and that's kind of what we are characterizing. So we are not trying to pitch this, right? We are proving that this is what happens.
Oh, I see. But,
so it's not like I'm advocating it. It is what happens when you train.
Yeah. So it looks like more. It seems like the two matrices should be like multiplied together, not like added.
No, I mean I see your point, but what's happening is that basically this WFIN and WSVM, they are living in different orthogonal subspaces. So in some sense, like there's a subspace decomposition as well, which I didn't discuss. But so basically, in one subspace, you're essentially kind of like separating relevant and irrelevant tokens, and the other subspace, you are kind of weighting the relevant tokens. Yeah.
So
Yeah.
this kind of decomposition can disperse for more efficient training on material.
Absolutely, yeah. And this is essentially kind of one reason, indeed, because like this WSVM should go to infinity, right? And controlling that is kind of the intuition behind like this adding gating, so that you don't need to let it go to infinity, but you can instead let the gating go to infinity, which is easier for the model.
Is the optimization problem based on the Softmax?
It is based on Softmax.
It's convex, right?
It's not convex, no. Yeah, in fact, it's. I mean, compared to this, it is actually much more complicated than this. I mean, if I want to state actual results, like, yeah, you would be sleeping a bit. Yeah. So essentially the optimization, depending on how you start and so on, it can converge to multiple different SVM formulations. But this is essentially kind of, and some of these are fully formalized, some of these are conjecture, because there are also convex settings. But long story short, in general, there can even be multiple SVM formulations. The model will converge to one of them.
But in one of your papers, the title is you show that it's equivalent to the support vector machine, right? Support vector machine problem.
Support vector machine, yeah.
It's convex, right?
Support vector machine is convex,
Yeah.
right? But there can be multiple such problems, and optimization can converge to solution of one of them. Yeah. But we also identified in another paper, like, I mean, in this paper, for instance, we have a like simpler setting, and in this simpler setting, the whole problem is convex, and we can characterize everything, and there's a unique solution.
Okay.
Yeah.